Okay. So yeah, so first of all, I'm not going to be talking about gamma ray burst or quasar flux data today. What I'm going to be doing is I'm going to be giving some background information on and summarizing the findings of a paper that I published last year in the monthly notices of the Royal Astronomical Society in collaboration with Yoon Chen and Bharat Ratra. So in that paper, again, true to my title, in that paper, we looked at expansion rate, baryon acoustic oscillation, and quasar angular size measurements. And one thing before I start, I don't know why my images are a little bit darker than what I intended them to be. You notice there's kind of this gray background here. I'm not sure why that happened, but I've checked all of my slides and everything is, legible and visible. It's just my images are a little bit darker than I thought they were going to be. But anyway, everything should still work out okay. Okay, so first, I want to give a little bit of background on just basic cosmology, right? So one of the fundamental things that we observe about the universe is that it's expanding on large scales. This is something that we've known for quite a long time. So what exactly does that mean? Well, you can kind of visualize the expansion of the universe in this way. This is an image that I took from Daniel Bauman's cosmology lecture notes, and I kind of like this way of visualizing it. If you think of, say, a pair of galaxy clusters, and you imagine that you have one, say, right here, and one, say, right here, and so again, you can imagine galaxy clusters kind of arranged on this coordinate grid. And as time goes on, the grid itself expands, right? So that's what we mean when we say that the universe is expanding, is it's not so much that matter on the largest scales is moving relative to the grid or relative to the coordinates that we've chosen. It's that the coordinates themselves are scaling up with time, right? So those galaxy clusters will move apart, but they maintain the same coordinates. As you can see along the horizontal axis, the coordinate separation between these two hypothetical clusters is still 1, but the physical distance between them increases. And so we can describe that mathematically using this equation. Physical distance, which I'm calling x subscript p, is related to the coordinate distance according to, well, it's related to the coordinate distance by this equation, where the scale factor, a as a function of t, changes with time, right? So again, the distances between things like galaxy clusters on large scales literally just get scaled up with time. It's a uniform expansion. Now, the interesting thing about the scale factor is that you can relate it to a quantity z, which is known as the redshift. And this is how you connect theoretical cosmology with observational cosmology. Because we have this relation between the size of the universe at a given time and the redshift that we can directly observe. I mean, again, if you look out into the sky and you look at, say, for example, again, a distant galaxy cluster, you can measure through various means, which I won't get into in this talk, but you can measure its redshift. You can measure the shift of its spectral lines toward the red, infrared end of the spectrum, and that tells you the scale factor at a given time. So again, this is how we relate the size of the universe to things that we can actually measure. Okay. And it turns out that if you apply Einstein's equations to the universe as a whole, if you apply Einstein's equations to a homogeneous and isotropic universe, which again is what we observe, then what you find, and again, I won't go through the derivation, but what you find is that you can derive these essentially equations of motion for the scale factor. You have these two equations, which are called here and here, which are the first and second Friedmann equations, that describe how the scale factor changes with time. And so the first term here, this rho, is just the matter density. And the second term in the first Friedmann equation is a function of the curvature of the universe. And I'll get into that in just a moment. But the key point I want to highlight here is that the evolution of the scale factor is determined by both the matter content of the universe and its spatial curvature. And the second Friedmann equation tells us that the change of the scale factor, or the second derivative of the scale factor, is related to the sum of the matter density and the pressure. And again, I'll go into more details about this in just a moment. Now, in these equations, we can define a quantity called the Hubble parameter, h is a function of t, which is just defined as a dot over a. So the rate of change of the scale factor divided by the scale factor itself. And this abbreviation will be extremely important as we go on, because one of the data sets that we looked at in our paper consists of measurements of this quantity, h of t. And so again, so this is something that you can directly compute theoretically, and we did that and we compared it to measurements. So I'm lingering on this thing because I want you guys to remember this equation, because this is extremely important. And the matter density in these two equations, the first Friedmann and second Friedmann equations, this rho depends on, I called it a matter density, but it's really more accurately called an energy density, because it depends on the density of non-relativistic matter, photons, and the energy density of dark energy. So those are the Friedmann equations, and so these are the equations for the dynamics of a homogeneous and isotropic universe. Okay. So I said that I would talk a little bit about the curvature of the universe. So this image, which again I took from Daniel Bauman's cosmology lecture notes, what this represents is a series of spatial slices through a four-dimensional space-time. So on the horizontal axis, so the horizontal axis going vertically upward in each of these diagrams is time. And these two-dimensional planes represent, spatial sections of the universe. Again, I can't draw a four-dimensional universe, so this is the best we can do. We can imagine that each two-dimensional plane really represents a three-dimensional space, and as they move upward along the vertical axis, they're moving through time. So each of these diagrams represents three possible ways that a homogeneous and isotropic universe can be curved on large scales, spatially curved on large scales. So you can have a flat universe where k equals 0, and by the way, k in this equation, again, refers to the k in the Friedmann equation. So you can have a universe which is flat on large scales where k is 0. And if you want to operationally define this, you can just imagine, say, if you were to draw a really big triangle on one of these spatial sections, then the sum of the angles would be 180 degrees. Or alternatively, you could say that light beams will not, say, converge if you fire them away from each other. So that's a flat universe. You can also have a negatively curved universe, which the spatial sections have this kind of saddle shape. Or you can have a positively curved universe, right, where spatial sections kind of look, convex like this. In 3 dimensions, a positively curved universe has the same curvature as a sphere, right? Whereas a negatively curved universe has the same curvature as a hyperboloid. So again, that's kind of a visual picture of what I mean when I say that the universe is either curved or not curved on large scales. Okay, now I said earlier that the expansion of the universe is a very important and well-known experimental observational fact. Well, another extremely important observational fact is that the universe is accelerating today. This was discovered about 20 some years ago, 22, 23 years ago. And one of the biggest challenges for cosmology today is to explain, okay, why is it accelerating? Why we can observe that it is accelerating, and in this image that I've taken from Scott Dodelson's cosmology textbook, we conclude that the universe is accelerating based on this magnitude redshift diagram. Now, what this is a diagram that represents the magnitude or the brightness of supernovae observed as a function of redshift. And depending on your cosmological model, you can predict how bright those supernovae should be at a certain redshift. And what people found, the people who discovered the accelerating universe, is that those supernovae were a little bit dimmer than what they would have been if the universe didn't contain a cosmological constant. Whereas if they put in a cosmological constant, they could fit that supernovae curve pretty well. And here on the bottom panel is a plot of the residuals. So yeah, so that's what I mean when I say the universe is accelerating. And we're still trying to figure out exactly what's powering it. So now, to get a sense of the physics behind an accelerating universe, we have to go back to the second Friedmann equation, which I've rewritten here. So if you want to make the universe accelerate, you need to add in basically an extra form of energy that has a peculiar negative pressure, and with a pressure less than negative ρ/3, where ρ is the energy density. So that's kind of the origin of the cosmological constant. Is it's an energy density that has a pressure that is related to, or the cosmological constant has a pressure that's related to its energy density in this way. And in other words, you wouldn't be able to get an equation of state like this if you just had a universe filled with matter, because again, non-relativistic matter has a vanishingly small pressure. So we can define a quantity, which I think I just mentioned, which we called the equation of state, and it's just equal to the ratio of the pressure to the energy density, right? So depending on your cosmological model, you can characterize your cosmological model by its equation of state. So the standard cosmological model, which we call lambda CDM, where lambda stands for, lambda is the symbol that we typically use to represent a cosmological constant, and CDM just stands for cold dark matter, meaning that we think that most of the matter in the universe consists of, well, cold, i.e. Having very low pressure, dark matter. And in the standard lambda CDM model, the equation of state is constant. It does not evolve with time, and it just has the value equal to -1. You can extend this model in a couple of different ways, and this is what we've done, and this is what I've been doing for the last several years. You can consider a model that we call XCDM, and this is just and I'll get into a little more detail about this in the next couple of slides, but this is basically just adding in some time evolution to the standard model, right? The energy density of the dark energy in the XCDM model evolves with time. It's not constant. And it no longer has an equation of state equal to -1. You can also consider a model which is called phi CDM, where phi, we just use that symbol to represent a scalar field. And in that case, you have a time evolving energy density, and your equation of state also evolves with time. So, okay. So now, before I go into those details, I need to define a few more symbols, which again, these will be important later. So for convenience, we typically define a function called the expansion parameter, which is basically just a dimensionless Hubble parameter. Again, as a reminder, the Hubble parameter h of z is just the is just the rate of change of the scale factor divided by the scale factor. So again, it's just telling us the expansion rate of the universe. And here I've written it as a function of redshift instead of time, but that's a pretty trivial transformation. And in order to get the expansion factor, I've just divided out a quantity known as the Hubble constant. Now, the Hubble constant is extremely important in cosmology because it's equal to the value of the Hubble parameter in the present, right? So it's equal to the value that the Hubble parameter has right now, or at least, at our current epoch. So it quantifies the expansion rate of the universe at the present. And we can use it also to set the scale for the age of the universe at the present and its present size, right? So the Hubble parameter sets a lot of really important scales in cosmology. So it's one of the parameters that a lot of cosmological studies try to fit. And it's one of the parameters that we're going to be fitting as well. Another extremely important parameter that most cosmological studies will try to fit to data is this omega fraction, which I'm defining here. Now, omega is this capital omega. That's just a dimensionless energy density. So you can, for each species of energy that you can define, say non-relativistic matter, photons, dark energy, what have you, you can define a quantity omega, which is just the energy density of that species divided by what we call rho c. And this is just the energy density. Well, this is just an energy density defined as 3h naught squared over 8 pi g. Again, this is just basically just a convenient rescaling in order to get dimensionless numbers. And it's also important to point out that these dimensionless energy densities add up to 1, right? So these are some key equations that show up, or well, maybe not show up a lot, but are the foundation of a lot of observational and theoretical cosmology, right? The relation between the energy density and the Hubble constant. Okay. So now we're getting into the connection between theory and measurements. So again, I just defined this expansion factor, which is, again, the Hubble parameter divided by the Hubble constant. So depending on your model, depending on your cosmological model, you can compute a different expansion factor, right? So for example, if we have a universe that consists of non-relativistic matter, and it has some curvature, and it has some dark energy in it, then we have an expansion factor. Oops, I went ahead too far. Then we have an expansion factor that has this form. And we can rewrite it if we want to explicitly incorporate, or if we want to explicitly show the dependence on the redshift, then we can rewrite it in this form, where this omega m0 is the present value of the non-relativistic matter density. Omega k0 is the present value of the quote unquote energy density due to curvature. I don't think I talked about this earlier, but when we incorporate curvature, spatial curvature into our model, then that shows up as a kind of an energy density, or rather we can sort of define it as a quasi energy density because it goes into the Friedmann equation in kind of the same way that the energy densities of other things do. So whenever you see this omega k0, that's really just telling you about the curvature of the universe, right? How much curvature does it have? And again, we also have this dark energy density. And just as a reminder, we derive this equation again from this extremely important connection between scale factor and redshift, combined with combined with this. So again, so this is how we connect our cosmological models to measurements. Okay. So now to get into the specifics, for each of the models that we looked at, again, we have 3 different expansion factors, right? So for lambda CDM, which again, just in our case, just consists of non-relativistic matter, some amount of curvature, and a cosmological constant, we have this expansion factor. Now, I should point out that the reason why there isn't the reason why we're not incorporating radiation into our energy budget is that, the observations that we're using were taken at relatively recent times. That is to say, relatively low redshifts. And at low redshifts, radiation is really negligible in comparison to non-relativistic matter and the cosmological constant. So we just don't incorporate it into our studies. And one key thing to note here in the lambda CDM model, if you have a cosmological constant, the energy density is, well, it's constant, right? It doesn't change with the redshift. In other words, it doesn't change with time. So that's kind of the key distinguishing factor of the lambda CDM model. And I said before that if you want to extend lambda CDM, one way to do it is to incorporate some time evolution of that cosmological quote unquote constant. And you can do that in a simple way by changing the equation of state. So we might ask ourselves, okay, well, does the equation of state necessarily have to equal -1? Which again, -1 is the value that it has for a cosmological constant. Well, if it doesn't, if it has some different value, then our expansion factor looks like this. So again, we have matter, we have curvature, and now we have this what is typically called an X fluid because it's, we model the dark energy as an ideal fluid in this case, that now has some energy density that depends on time. And you can see here that if Wx were equal to -1, then we would just have 0 in this exponent here, and then we would reduce back down to lambda CDM. So again, XCDM is just a simple extension of lambda CDM that allows for some time variation. And if we, depart even further from lambda CDM, we get phi CDM, which again, I said before, is what we do in phi CDM is that we model the dark energy as a dynamical scalar field, right? So instead of just saying that it's some constant energy density that sort of permeates the universe, in phi CDM, we have a dynamical scalar field that permeates the universe. And so we parameterize the energy density of that thing in this way. And, if you have a dynamical scalar field, you don't have a straightforward relationship between energy density and redshift. You can compute it, but you can't write it down in a simple form like, like this or like this. But either way, the point is that you can compute the energy density of the scalar field as a function of redshift. And so in turn, you can compute the expansion factor. So again, you can compare observations to theory. So a little bit of detail on phi CDM on the scalar field. So if we say that the dark energy is modeled as a spatially homogeneous scalar field, that is to say that it only depends on time, then we can associate an energy density with it that looks like this, right? And this, this looks pretty familiar. I mean, you essentially have a quote unquote kinetic energy and you have a potential energy, right? So we can associate an energy density with the scalar field. And the potential, the particular potential that we've been looking at goes like this, right? So it's proportional to phi to the minus alpha. So the key parameter in the phi CDM model is alpha. And I want to go back very briefly to my previous slide because I want to highlight what the key parameters of each of these models are. So the key parameters in lambda CDM are omega m and omega k and omega lambda. In XCDM, the key parameters are, again, omega m, omega k, and the equation of state here. And in phi CDM, the key parameters are omega m, omega k, and alpha. So the exponent that controls the shape of the potential. Okay, so that's phi CDM. And if you work through the math, if you plug this scalar field into Einstein's equations, then you can derive an equation of state for the field. And what you notice is that this field is coupled to the expansion of the universe. It has it has this term in the middle which sort of looks like a friction term almost. So you can solve this equation of motion for the scalar field in tandem with the Friedmann equation for the scale factor. And you have to solve them in tandem because they form a set of coupled differential equations. Because if you notice here, the energy density of the scalar field factors into the Friedmann equation. So again, you have to solve these at the same time, which we solve them numerically. But again, you can do that. It takes some doing, but it's doable. And then again, if you do that, you can compute an energy density. You can fit theory to data. So this is what we do. This is what we work with. Okay, so let's see. How am I doing on time? So the data that we collected for this paper consists of 162 measurements. So we have 31 measurements of the Hubble parameter, which again, remember, the Hubble parameter measures the expansion rate of the universe. We have 11 baryon acoustic oscillation measurements, which I'll talk about those in just a minute. And we have 120 quasar measurements, quasar angular size measurements, which again, I will also talk about those in just a minute. And these are the papers from which we, down here at the bottom, these are all the papers from which we took our measurements. Okay, oops. Okay, so baryon acoustic oscillations are, the physics of baryon acoustic oscillations is actually quite interesting. So in the early universe, what was going on was oscillations in the coupled photon baryon plasma that existed at that time. So you can think of this as a sort of a competition between gravity, which is pulling things together, causing things to collapse, and radiation pressure, which is pushing things apart, right? So you have these two competing forces. And as a result of that, you get oscillations, right? Baryons want to clump together through gravity, but as they get too close, radiation pressure pushes them apart, so they fluctuate. And you can see this in both the cosmic microwave background and in the matter distribution. So this is apparent both in like I said, in the distribution of galaxies, and it's also apparent in the CMB. So if you look at the CMB, this is, you see something that looks like this. And so again, this image comes from Daniel Bauman's cosmology lecture notes. What you're looking at here are essentially the correlation coefficients between the temperatures measured at two spots on the sky. And so if you fit those using spherical harmonics, what you find is as a function of L, in other words, as a function of angular separation, you find these characteristic oscillations. For our purposes, though, and the measurements that we use are all based on the baryon acoustic oscillation signal in matter. And so what that looks like, so I've got this kind of schematic illustration here that I took from this very nice review article on arXiv. So on the left panel, what is represented is, say, a hypothetical galaxy distribution where what they've done is they've sort of exaggerated the baryon acoustic oscillation signal. So what you can see here is kind of a series of, you can kind of see a series of rings here. You know, sort of, you can see kind of these correlations that show up in the galaxy distribution. And so what that's meant to represent is, you know, is the remnants of those acoustic oscillations that I talked about earlier. Because what happens as the universe expands, as it evolves, those acoustic oscillations, you know, again, early in the universe, you've got baryons and photons oscillating together. Well, what happens is after recombination, which is, you know, when electrons find nuclei, basically, and they combine, the universe becomes neutral. So the photon pressure disappears, but the remnant of the acoustic oscillations is still frozen into the matter distribution. And so, you know, what happens is that you know, that as matter continues to evolve, you know, more and more bits of matter will sort of clump together on a scale which is set by the size of those acoustic waves. Now, if you were able to actually see that scale, again, you would see something that kind of looks like this. But it's not this simple. What you actually see is something that looks like this kind of noisy, you know, featureless mess on the right. But it turns out that you can extract the baryon acoustic oscillation signal, you know, if you analyze this statistically, and this is exactly what people do. So that's how that works. And so when you analyze that signal statistically, what you find is that, again, you have this sort of preferred scale, right? So in other words, if we think of this ring as sort of like a ring of, you know, galaxies, again, what you find is that galaxies sort of like to clump together in this preferred formation, right? They quote unquote like to clump at a certain distance from each other. And if you can calculate that distance, what you have is what's called a standard ruler, which can be predicted from theory, and then, you know, you can compare that to the measurements that you make. So again, the point is that with baryon acoustic oscillations, you know, after those oscillations sort of freeze out, they are still imprinted on the matter distribution, and if you can pick out the scale of those oscillations from the distribution of matter, then you can compare that scale to what you predict from theory. So that, you know, that's the take-home point here. And again, this is what we do. So, you know, if you measure, you know, you can measure the scale in a couple of different ways. You know, you can measure the sort of transverse scale here, which gives you an angular size distance. You know, or you can measure this sort of parallel scale, which gives you information about the Hubble parameter. And, you know, like I said, there are a lot of different ways that you can do this. So let's see, I don't know how much time I want to spend on the details of these distances that you can measure. The only point that I want to highlight here is that from the analysis of baryon acoustic oscillations, you can derive different distances that you can then compare from theory. So this is an example of the various things that you can derive. So again, from this picture, we have an angular size distance, which is dA, which we can use that to compute co-moving distance dm. And we can also combine that with the expansion factor to form this distance scale dv, which is, you know, some people do that, and again, it's something that you can compute. So again, the point is that there are various distance scales that you can calculate with baryon acoustic oscillations that you can compare to theory. Okay. So that's how that works. And now here's, you know, so the connection with theory comes in this way. So remember I said earlier that the expansion factor EZ depends on the parameters of the cosmological model that you're considering. So if you have a given model, then you can compute a distance, which I'm calling dc, as a function of those parameters. And depending on the model, that distance will be different. And again, you can compare that to theory. And depending on how much curvature you have, this function might be a little bit different. But again, the point is that you can compute distances from theory and then compare them to measurements. So hopefully that's straightforward. Hopefully that's clear enough. So the measurements that we used for this paper I have in this table. Now, all of these measurements are scaled by what's called the sound horizon distance, which is this quantity here, which the sound horizon distance is basically just the greatest distance that an acoustic wave could travel from the beginning of the universe up until now. Right, so again, it kind of sets the scale for baryon acoustic oscillations. And you'll notice from this table that almost all of these measurements are actually scaled by a ratio of what's called the fiducial sound horizon distance over the sound horizon distance. And the reason for that is, whoops, went too far. The reason for that is that in order to actually extract measurements of baryon acoustic oscillations, what you have to do is you have to assume a fiducial model in order to translate from redshift to distance. And so what people do in analyzing the matter distribution on large scales is that they can compute what they do is they compute a power spectrum, right? So they can extract the oscillation signal, but in order to translate from what they actually observe to these measured distances, they have to kind of assume a model. But what they do is that they say, okay, given a fiducial model, we can translate from redshift to distance. And our power spectrum depends on these ratios like this between, say, the distance in the true model and the distance in the fiducial model that we've assumed. So what they do is that they fit these alphas, they fit these quantities, alpha parallel and alpha perpendicular. And those quantities essentially, they quantify the deviation of the observed distance from the fiducial model distance, right? So there is a little bit of model dependence in these data, but that turns out actually not to be that big of a deal. People have studied this and found that for different combinations of different types of fiducial models, you still get roughly the same predictions. So this is something that we aren't too worried about at the moment, but I still thought I should point out that this is how you actually measure it. But anyway, so that's what people do. That's how they get those distances that I was talking about. Okay. So now on to Hubble data. So the Hubble parameter data that we use is I've reproduced in this table on the right. And so these are, so what I should point out is that all of these measurements and uncertainties have units of kilometers per second per megaparsec. So again, what that means is that sort of the expansion rate as a function of the size of the universe. But again, the point is that, all of these measurements are things that you can directly relate to the expansion factor or the expansion rate, which again, you can compute from theory. And what we do is we just fit the Hubble constant here. Whoops, went too far. So how do people actually measure the Hubble parameter? Well, if you write the Hubble parameter strictly in terms of the redshift and time, if you have a relationship if you have something that you can observe at a known redshift, and so if you have a known redshift, or at least a known redshift difference, and you can relate its age to the redshift, then you can directly compute the Hubble parameter that observable. So what people have noticed is that if you look at the spectrum of what are called massive and passive early type galaxies, that is to say galaxies that are, well, massive, but are passive in the sense that their star formation rate, or that they're no longer actively forming stars, what people have found is that there's a simple relationship between the age of those galaxies and a feature in the spectrum called the 4,000 angstrom break. So that's just a discontinuity in the spectrum at 4,000 angstroms, the amplitude of which is linearly related to the age of the galaxy. And the slope of that relation the slope of that relation does depend somewhat on the model that you choose for the star formation history and the metallicity of the galaxy, where again, metallicity just refers to the composition of the galaxy, the chemical composition. So metallicity is just how much stuff in the galaxy do you have that's not just hydrogen. But again, what people have found is that this slope tends not to be strongly dependent on models of star formation history and metallicity, and the uncertainties that we're working with, the uncertainty budget that we're working with has already accounted for those differences. So again, if you have this 4,000 angstrom break, so you can plug this into your Hubble parameter equation, and what you find is this, and you can directly measure the redshift difference between two different galaxies, and you can measure the difference in their amplitudes, or difference in the amplitude of that 4,000 angstrom break. And if you have a pretty good idea of what the slope is, then you've got a Hubble parameter. So that's how people measure that. And if you want more info on that, I've got some references here. So the third observable that we looked at is angular size data from quasars. So what people have found is that if you take a sample of intermediate luminosity quasars and you measure the distance from the core of the quasar out to the point where the jet becomes dim enough, then what people have found is that that feature, that size of that structure, tends not to change very much within that sample. And so again, it furnishes another kind of standard ruler. And again, standard ruler in the sense that it doesn't change between different populations of things. And so you can relate so what that standard ruler gives you is a prediction of an angular size. So you can predict theoretically the angular size of a quasar following this equation here. So the angular size is just, again, that standard ruler length divided by angular size distance, which, remember, angular size distance is something that you can compute from theory. So again, we have another relatively straightforward connection between theory and observations. So now how do people actually get that intrinsic length scale? Well, so what they do is they essentially use what's called a Gaussian process method to reconstruct the Hubble parameter from cosmic chronometer data. So there is some correlation between quasar angular size data and Hubble parameter data. But what they do is they essentially interpolate the Hubble function, hz, then they use that to reconstruct the angular size distance, which then they compute the intrinsic length scale of the quasar, and then you can translate that into measured angular size. So again, there is a bit of a correlation between quasar angular size data and Hubble data, but at the moment, the error bars on our quasar data are still pretty big. So at the moment, we're not too worried about that. But anyway, that's how people get that scale. And I think this is just a list of the data that we use. I'm not going to spend too much time on this, but if you want to look into this more carefully, this is the reference to look at. We took our data from this paper, And again, I can come back to this if people want to see it. Okay, so in the interest of saving time, I'll accelerate a bit. So to analyze the data, we basically just did a chi-squared fit, right? So you've got, you know, uncorrelated chi-squared fit, which is pretty straightforward, and a correlated chi-squared fit, which has this form, right? So you've got a data vector difference between theory and observations, and you've got an inverse covariance matrix. So only a handful of our measurements were correlated, and that was some of the BAO data that I showed you. And you know, this is our covariance matrix, which we just got from the SDSS website and which we reproduce in our paper. But so again, the point is that we can account for these correlations. Oops, went too far. And again, if you have a chi-squared function, then we can define a likelihood function according to this relatively standard formula. And you can marginalize that likelihood if you want to extract information about specific parameters, right? So if you want to marginalize over a prior, or if you want to marginalize over one parameter to get constraints on another parameter, then you do that just by integrating the likelihood function. And you'll see those contours in just a moment. And so all we did was we just recorded the cosmological parameters that give us the smallest value of chi-squared. And we also looked at quantities. We also looked at the Akaike information criterion and the Bayes information criterion. So what these do is they quantify, well, they essentially quantify Occam's razor, right? Because you can get, if you have a model that has, say, 1 million parameters, well, you can fiddle with those parameters until you get an extremely small chi-squared, but you won't really have achieved a good fit. You won't have learned anything. So, we generally think it's best to explain the data that we have with as few parameters as possible. So what AIC and BIC do is that they punish models that have too many parameters. So here, K is the number of parameters and N is the number of data points. So we looked at chi-squared and we also looked at AIC and BIC, just to make sure that we weren't, overfitting our models. Okay, so now here's, after 15 minutes, here's where the actual results of the paper are. So for flat lambda CDM, so in two-dimensional parameter space, we have these constraints on the left. And so the dotted contours refer to quasar data just by themselves. The dashed contours refer to HZ plus BAO data, and we combined those two so that we had, so that we didn't have plots that were too cluttered looking. So again, we have quasar data and we have HZ and BAO data, and when you combine them, you get the solid lines. So what we see from this fit is that just from these three sets of data, we have a pretty tight fit to the parameters of flat lambda CDM, those being the matter density and the Hubble parameter. And so we find that the Hubble parameter, the best fit is about here. So it's just under 70 kilometers per second per megaparsec. And the best fit to the matter density is about here, just a little over 0.3. And again, you can see that from the one-dimensional fits here and here. So that's good. I mean, because this value of the matter density is pretty standard. This is what you typically expect to find. And what's interesting about this is that what's interesting about the fit to the Hubble parameter is that the value that we obtained in this fit is closer to the value that you get if you measure the Hubble parameter using data from the early universe. So you can measure the Hubble parameter using CMB data, for example, and you get a value that's sort of close to what we got. You can also measure the Hubble parameter using what are called late time measurements, that is measurements of things like supernovae, which are at relatively low redshifts compared to the CMB. And if you do that, then you get a value of the Hubble parameter that's right around here. So what we found, at least for flat lambda CDM and for several of our other models, is that the data, using the data that we have, we get a value of the Hubble parameter, the expansion rate of the universe at the present, which is a lot closer to what you would expect from CMB data. So, you might have heard of the so-called Hubble tension, where early measurements and late measurements of the Hubble parameter kind of disagree with each other. Well, what we're finding is that the Hubble parameter, at least from the data that we looked at, agree better with the early measurements. So you can also look at constraints from non-flat lambda CDM, which is where we allow spatial sections to be curved, and the results of that are not too different. Again, we find a matter density which is close to about 0.3. We find a Hubble parameter which the central value of which is just under 70 kilometers per second per megaparsec. But again, in this case, we have a little bit of flexibility in our model to the point where we can still incorporate a higher value of the Hubble parameter, but it's still less likely than a lower value would be. And we also find that the data favor a slightly closed universe, although not by a lot, because if you look on the upper left panel here, what you find is that the confidence contours in our parameter space, again, these are 1, 2, and 3 sigma confidence contours, you find that they pretty well overlap with this blue dashed line, and any points along this blue dashed line refer to a flat universe. So they pretty well overlap with spatial flatness, although there is, again, some preference where this red dot is our best fit point. There is, again, some preference for a closed universe, but not by much. And the constraints from flat XCDM are kind of similar. Again, we apparently slightly prefer a closed universe, but not by much. Our Hubble parameter, the best fitting value is still closer to the early type measurements. But again, in flat XCDM, because we have more parameters, our constraints are a little bit wider. So now we have a little bit more room to accommodate a higher H0 value. And in a flat XCDM, we also find that the equation of state is most likely to be close to -1, right? Because our confidence contours pretty well overlap with the lambda CDM line here. Although there is some slight preference for a value that is different from lambda CDM, but not by much. And if we allow spatial sections to be non-flat, if we allow curvature, then our constraints deviate a little bit more from what's expected, because we expect, because the consensus model of the universe is that it's probably flat on large scales. Well, if you fit the data using a flat XCDM model, what you find is that there is a little bit more preference for curvature. And you also, interestingly, find that there's a little bit more preference for a value of the equation of state, which is different from a cosmological constant. And you can see that here, you can see that here. You can see both of those effects here in this plot. And you can also see that at the very least, the 3 sigma contour overlaps pretty well with the late time value of the Hubble constant. So again, if the point is that if you fit the data using a non-flat XCDM model, then you have quite a bit more room for extensions to the standard model. These being curvature and values of the equation of state that are different from -1. And you can see that a little more clearly in the one-dimensional fits as well. But I think I'm running out of time, so I don't want to spend too much time on those. If you look at the flat phi CDM constraints, what you find is that the value of alpha, the parameter that controls the shape of the potential energy, that's pretty close to 0. And if you have a value of alpha that's 0, then you just have lambda CDM. So phi CDM reduces to lambda CDM when alpha equals 0. So what we find is that there is, some possibility that alpha is different from 0, but our best fitting points are all pretty close to 0. And we also find relatively narrow constraints on H0 and we find relatively narrow constraints on omega m. Omega m, by the way, is the most model independent parameter that we have. Out of all the models that we considered, almost, they all pretty well predict a value of the matter density that's roughly close to about 0.3 with relatively narrow error bars. So I think that's a pretty clear indication from at least the models that we looked at that, omega m is probably pretty close to 0.3, which is what other studies have predicted as well. Okay, so again, just like with non-flat XCDM, if you open up the parameter space to allow curvature, then your error bars get a bit wider. You can allow for a little bit more room for a higher value of alpha, and we also find pretty strong, well, not strong, but we find some preference for non-flatness, spatial curvature. But again, it's not a huge effect. So that the sort of takeaway from all of this is that we do find some indications from the data for extensions to the standard cosmological model, but they're not decisive discoveries by any means. And I don't think I have enough time to dwell on these best fitting parameters, so I'll just kind of skim through them. So our conclusion, again, as I was saying, we have some marginal evidence for extensions to the standard model, like spatial curvature. We have some marginal evidence for dark energy dynamics, but again, not really decisive. What is a bit more interesting is that our H-naught, across all models, our H-naught ranges from around 1.9 sigma lower than supernovae measured values of H-naught to around 2.5 sigma lower than supernovae measured values of H-naught. So, across all models, what we find is that there's a bit of a preference for a lower value of H-naught. That is a value of H-naught that is more consistent with CMB measurements. And that's important because all of the measurements that we've taken are at relatively low values of the redshift. That is, they are themselves relatively late time measurements. But we find that they agree decently well with measurements of H-naught that are based on high redshift observables, early time observables like the CMB. And again, I didn't write this down, but also our matter density across all models is pretty close to around 0.3 with relatively narrow error bars. So that's another sort of model independent result, which again gives us evidence for dark energy. Okay, so that's pretty much it, and I think I'm exactly at 2 o'clock according to my watch. So I will just take the next few seconds to thank Chang-Gyung Park and Lado Samusha for helpful discussions, Dave Turner of K-State for helping me out with the computations, and my current collaborator, Shulei Kao, for pointing out a mistake that I made in earlier version of the paper, and funding information down here. And we are funded by the Department of Energy, and we have some other funding information there.